Of Unit 4. And Unit 4 is all about radical functions and rational exponents. In Learning Target 6a, we're going to learn about the connection between a radical expression and an exponential expression. By the end of this lesson, you will be able to apply the concept of nth roots without a calculator to solve problems. You will be able to simplify radical expressions and apply the properties of rational exponents and see their connection to our nth roots. So let's start with what an nth root is. So the nth root, if I have a to the n equals some other number b, then a is what we call the nth root of b, and it is written as a equals this nth root of b. And we're going to talk about in more detail down below what each one of these pieces is referring to. So in this nth root of b expression, the n is what we call the index. The square root symbol that we're used to seeing as only a square root is really just a radical sign. And what type of root we get is based off of the index. And the stuff that's underneath the radical sign is what we call a radicand. So up until now, we've always looked at this where we have a square root. And in that case, our index is assumed to be 2. And we actually never wrote anything in the index spot since it was our most basic case being a square root. Now, if our index becomes a higher power, if our index is a 3, we call that a cube root. And we would have a 3 written up there as that superscript, so it would be like the cubed root of b here. For any index that is 4 or higher, we don't have any special names for that. We would just call that the 4th root, 5th root, 6th root, 7th root, etc. And what those would look like then is I would have a 4 as my index, and then the radical symbol to mean the 4th root, and then whatever's inside, so I'll just keep it the same with this b value. And we could also see that for a 5th root of b, and so on. But if no number is written there, it is still what we would assume to be our square root. And so if our index is 2, that is still our square root, and we would not write any number in the spot of the index. Now you're probably wondering, well, what the heck are we talking about radicals now? Our whole prerequisite for Unit 4 had to do with properties of exponents. Well, radicals and exponents are actually connected and they're alternative forms of one another. So how do these two relate? So on the left side here, I have what we call the radical form, which is what we defined up above as the nth root of x. And then on the right side, I have the exponential form or the exponent form. And that would be equivalent to x to the 1 over n power. So this nth root of x is the same thing as x to the 1 over n power by definition. So this allows us to convert back and forth between radical form and exponential form. So all of our properties of exponents that we reviewed in the Unit 4 prereq video are going to come into play when we deal with radicals expressions and we change them into exponential expressions. And let's see just a couple examples of converting back and forth. So in our first 3 examples here, we're going to convert the following from radical form, which each one of them is in, to exponential form and simplify if possible. So in this first example here, we have what we say is the square root of 10. I have no number written in my spot of my index, so we assume our index is equal to 2 then, and we would pronounce this as the square root of 10. Now if I want to convert that to exponential form, I'm just going to rewrite it so that I have my rational exponent instead. And by definition, whatever our index is, our exponent becomes 1 over that index when we convert to exponential form. So the square root of 10 would be equivalent to 10 to the 1 over 2 power, since our index for a square root is equal to 2. Now we could do the same thing for a cube root. So here in example 2, we have the cube root of 4. Our index is that 3. And our radicand in this case is the 4. Remember, the radicand is the stuff underneath the radical symbol. And if we want to convert this to exponential form, our 4 is going to stay the same, so that becomes our base of our exponent. And our index becomes that 1 over 3 exponent. And on our last example here, we have the 4th root of 11. Our index in this case is equal to 4. And we want to write this in our exponential form instead. So just like we did in the prior 2 examples, I'm just converting between radical to exponential form, and I'm just practicing rewriting it. So here our radicand is 11. That becomes our base of our exponent. And then our index becomes 1 over 4, so 1 over our index as our exponent. And we're going to see this conversion back and forth between radical and exponential form throughout this entire unit. This is helpful in converting and just kind of rewriting depending on what we're trying to solve or what we're given in a problem. So let's look at how some of this will actually get simplified down, and we'll start seeing some examples. So if we take an nth root of an nth power, something special happens where the index and the power cancel out. And we've seen this happen before. We've seen it with a square root and a square. Those two cancel each other out. And the reason that that ultimately happens is that the nth root of b to the n, I could rewrite this as b to the n to the 1 over n, since that index of n here becomes my 1 over n exponent. And then using properties of exponents, we know that these reduce down. That can multiply them since I have power to power. And so n times 1 over n would just leave me with b to the first. Now, this gets a little tricky though, depending on what our index is. It's not always as straightforward as just canceling them. So if our index is odd, like in this first part of this function here, then that's exactly what happens. The index and the power cancel each other out if n is odd. Now, if our index is even though, we actually end up with the absolute value of what we started with. And I want to show this through two examples down below. So in our first example here, we're going to look at the case where the index is an odd number. And when that happens and our index is an odd number, let's look at maybe 3 as our index. Here I have the cube root of negative 2 cubed. So in this example, negative 2 is our b value. So I'm going to go ahead and highlight that original b value. Well, when we simplify these, negative 2 cubed would be negative 2 times negative 2 times negative 2, which would give us a negative 8. And then the cube root of negative 8 is equal to negative 2. Likewise, if I had the cube root of 2 cubed, now I'm starting with 2 being my original b value. 2 cubed is equal to 8 since it's 2 times 2 times 2. And then the cube root of 8 is equal to 2. So in this case, whatever number we substituted in to begin with, it was the same number that we got it out. So if I subbed in negative 2, I got out negative 2. When I subbed in positive 2, I got out positive 2. So when the index is odd, we end up with the same number we started with. That is this first case up here where we just get b back itself. Now, if our index is even, we have to be a little bit more careful because of how even powers work. So in this first example, we have the square root of negative 2 squared. Negative 2 squared is what I'm going to start by simplifying. So here negative 2 is our b value. When I take negative 2 and I square it, I get negative 2 times negative 2, which gives me a positive 4. Then the square root of 4 we know is equal to 2. So in this case, I substituted in a negative number and I ended up getting a positive number out. And the reason that happens is because ultimately I'm ending up with the absolute value of the number we started with. And the absolute value of negative 2 is equal to 2. We can look at the same case if I sub in a positive number here. I have the square root of 2 squared. So 2 is the number I'm subbing in as my b. 2 squared is 4. Square root of 4 is equal to 2. So in both of these cases, whether we sub in a positive or a negative number, I end up with a positive number out because of how even powers work. They always make everything positive. So this is this bottom case here where we end up with the absolute value of b if n is even. And this isn't something we've had to worry about before, and it's honestly something I don't have to worry about if I have numbers that are being subbed in because it's already going to work its way out as a positive number because of what happens when I square something. But the reason this is going to be important is we're not always going to have numbers that we're subbing in. We might have variables, and we don't know what those variables represent. And so in those cases, we're going to have to worry about if I get these absolute values or if I don't get these absolute values. And what it boils down to is if the index is even or odd. If the index is odd, there is no need to worry about absolute values. That's the first case that we have up here. But if our index is even, then I do have to make sure that my final answer has those absolute values on it. So let's look at simplifying some of these. So for all of these, we're going to simplify the following so that we have no radicals in our final answer. So in example 4, we have the square root of 25x to the 10th. For each one of these, before we start solving, I want us to identify our index. And it's going to be important to practice it because the concept of an index is something that's going to come up throughout the rest of this unit. So what is our index in example 4? So here in example 4, since I have no number written as a superscript by the radical symbol, we assume that it's a 2. So our index here is a 2. Another way to think about that is we know that this is a square root since nothing is there, and that would be by definition having an index of 2. Now let's go ahead and start simplifying it. We've got two pieces here. We've got the number or the coefficient part, and we have the variable part. Let's start with the coefficient. What's the square root of 25 equal to? Well, the square root of 25 is equal to 5. So we end up with 5 outside the square root then, and I'm just going to leave x to the 10th alone for right now. So in this first step, I've just simplified the coefficient part. Now we're going to start to think about our definition from up above of how to convert from radical form to exponential form, and I'm going to write it on the side just for us to remember. And so what it said up above is if I have the nth root of b, that is the same thing as saying I have b to the 1 over n power. And we're going to want to reference this throughout. So here, since our index is equal to 2, I still have the 5, but I can rewrite the square root of x to the 10th as x to the 10th to the 1/2 power. And I'm doing that since by definition the square root is the same thing as the 1/2 power. And notice the x to the 10th I put in parentheses since that's the only piece that's being raised to the 1/2 power. The 5 is not being raised to the 1/2 power because the 5 is outside of the square root to begin with. From here, we're going to want to go ahead and simplify down. Using our properties of exponents that we reviewed in our prereq video, we know that if we have power to power, we get to multiply those. So 10 times 1/2 is going to give me 5. So we end up with 5 times x to the 5th now from the 10 times the 1/2. Now in this case, since our index was equal to 2, that's an even number, so we have to worry about putting absolute values around our final answer. But we can think about this. 5 is already a positive number, so the absolute value around 5 is not doing anything. But since we don't know what the x is, we do need absolute values around the x to the 5th. And especially because if x were to be a negative number, any negative number to an odd power is still going to be negative, so we need those absolute values to make sure it would make it positive. And that will be our final answer. Okay, let's look at example 5. We have the cubed root of 8 times x to the 3rd, y to the 9th. Why don't you guys pause the video right now and write down what your index is equal to. So our index in this case is equal to 3. I'm going to point out that that is going to be an odd number. We're going to want to keep that in mind. We can simplify this similar to how we simplified example 4. We've got this coefficient part of 8, and then we have two variables here. Well, let's start with simplifying the coefficient part. What is the cubed root of 8 equal to? Well, the cubed root of 8 is equal to 2, since 2 to the 3rd power is equal to 8. So we can pull that 2 out, and I'll get 2 times the cubed root of x cubed y to the 9th power. From here, we're going to apply that definition of going from radical to exponential form. So I can rewrite that cubed root as the 1/3 power. The 2 will stay in front of it since it's not inside as part of the radicand. But x cubed y to the 9th is all inside my radical, so all of that will be raised to the 1/3 power. Now, something else that's coming from properties of exponents is we learned if we have two exponents that are multiplied that have different bases, I cannot combine these bases together since one of them is an x and one of them is a y. But what I can do is I can distribute the 1/3 power to each one. So I'll end up with x to the 3rd to the 1/3, as well as y to the 9th to the 1/3 as well. And from here, just like we did in the prior example, since I have power to power, we're going to go ahead and multiply those. So I get 2x to the 3rd to the 1/3 would just give me x to the 1st, and then the 9 times the 1/3 will end up with a 3 as my exponent. And since our index here was an odd number, I don't have any absolute values that I need to worry about in our final answer. Well, let's look at what happens if I have a fourth root. So here in example 6, we have the fourth root of x to the 12th times y to the 16th. Why don't you guys pause the video right now and write down your index and decide if that index is even or odd. So our index here is going to be 4 since it's a fourth root, which is an even number. If we have an even number as our index, are we going to have to worry about absolute values in our final answer? So yes, we will, so we'll have to keep that in the back of our mind as we start to solve this. In this case, I have no coefficients, so I'm going to go straight to rewriting this from a fourth root into a power. What power will I end up raising x to the 12th, y to the 16th to in place of that fourth root? Well, since our index is 4, and we know that the radical form from the index is equal to 1 over that index as an exponent, we end up with 1/4 as our exponent. Just like we did before, the x to the 12th and the y to the 16th can't be combined since the bases are different, but we can distribute that exponent to each one of these. And then from there, I can multiply them and we get x to the 12th to the 1/4. So 12 times a fourth is equal to a third. So we get x to the third, and then 16 times a fourth is equal to 4. So we get y to the fourth. And since our index is even, we're going to want to put absolute values around that answer. And I want us to think about this. So here I have an x to the third and a y to the fourth. Well, no matter what I sub in for the y value, we're raising it to an even power. And if I take a positive number to an even power, I get a positive number. And if we take a positive number if we take a negative number to an even power, I also get a positive number. So in this case, y to the fourth, no matter what I sub in, would always be positive. So there's actually no need to have the absolute value bars around the y to the fourth. I would just need them around the x cubed, since that cube is an odd power there. Okay, let's look at a couple more examples. So here in example 7, we have the fifth root of x to the 10th over the cubed root of x to the 12th. Well, this is a little bit different than what we saw up above. Here we've got two different indexes. We have an index of 5 for the top, and we have an index of 3 in the denominator. And if I have different indexes, there's nothing I can really do to combine those. So let's think about individually how I could simplify them. So why don't you guys pause the video right now and decide how you could rewrite the numerator as an exponent, and how you could then separately rewrite the denominator as an exponent. So in the numerator, since we have a fifth root, that would become the 1/5 power then. And since we have a cube root in the denominator, that would become the 1/3 power. From here, individually, I can simplify each one of these since I have power to power. So 10 times a fifth is going to give me x squared, and then 12 times a third is going to give me x to the fourth. And now I actually got rid of all of my fractional exponents. And we know that if I have the same base, I can actually subtract exponents. So I end up with x to the 2 minus 4 since it's the top minus the bottom, which leaves us with x to the negative 2. And we learned we never want to leave negative exponents, so I'm going to go ahead and simplify that down by flipping that back down to the denominator to get x to the positive 2. And in this case, since both of our indexes were odd, I don't have to worry about any absolute values. So we can see already lots of our properties of exponents are coming into play. That's such an important skill that we're going to use throughout the rest of this unit and later on in other classes and other units as well. Let's look at example 8. What's our index in example 8? So our index in example 8 is 3, which is an odd number. Are we going to have to worry about absolute values on our final answer? So we won't have to worry about absolute values since our index is odd. Now this looks similar to 7 because we have a fraction, but there's a subtle difference there. In 7, we have two different indexes, and in 8, I have the index over the entire fraction. So we're going to go ahead and start by simplifying the inside first before we apply the index. So let's simplify that down as much as we can. Now x to the 14th over x to the second, we can subtract those exponents. So I'd get 14 minus 2, which would give me an x to the 12th. And now this looks similar to one of the first couple examples that we saw. Why don't you guys pause the video here and finish solving this one out on your own, and we'll check it together. So the first thing I want to do is rewrite this cube root as the 1/3 power. So we'll get x to the 12th to the 1/3, and then we can multiply our exponents there to leave us with x to the 4th. And like we talked about in the beginning, since our index is odd, I don't have to worry about any absolute values. Let's look at example 9. So why don't you guys pause the video and write down what our index is in example 9, and then decide if you're going to have to worry about absolute values or not have to worry about absolute values. So here we have a square root, so our index is equal to 2, which is an even number. So we are going to have to worry about those absolute values at the end, so we'll just keep that in the back of our mind. I noticed a couple things about example 9. The first is I have a coefficient again, so why don't we simplify that right away? What's the square root of 4 equal to? Well, the square root of 4 is a perfect square. It's equal to 2, so the 2 comes out of the square root, and we get left with the square root of x cubed, x to the 5th, and y squared still inside. Now the next thing I'm noticing is I have more than one x to a power, and when we have the same base, we can actually combine those together. And if I have x cubed times x to the 5th, we add those exponents together, so I still have the 2 on the outside. Then inside the square root, the 3x cubed times x to the 5th will become an x to the 8th since we add those exponents. And then we still have that y squared. And of course, since the x to the 8th and the y squared have different bases, we can't combine those. But from here, we could rewrite this in exponential form. Why don't you guys pause the video and rewrite this as x to the 8th y squared, and then decide on what our exponent will be. So since our index is equal to 2, we'll get this raised to the 1/2 power, since it's always 1 over the index. And again, since both the x to the 8th and the y squared were inside the square root, then both of those are being raised to the power. Why don't you guys finish off this example on your own, and then we'll check it together. So from here, we can distribute that 1/2 power to be x to the 8th to the 1/2, y squared to the 1/2. So we still have 2. 8 times 1/2 is going to give us x to the 4th. And then 2 times 1/2 is just going to give us a first. So we end up with 2 times x to the 4th times y. Now because our index is even, I do have these absolute values that I have to worry about. And just like we saw before, well, 2 is already a positive number, so that can come outside of the absolute value bars. And then x to the 4th, no matter what I sub in and raise to an even power, so in this case 4, will always come out positive. So the absolute values around the x to the 4th is a little redundant and unnecessary since it's already a positive number itself. But the y value, since that's being raised to an odd power of just 1, we do have to leave the absolute value bars around the y in case y were to be a negative number. Now we're going to look at 2 final examples, and we'll notice that they're a little different than what we've seen prior. We have no variables here, and that's on purpose. These are a little bit different, but they still relate to this concept, and it's important to know how to simplify something like this without a calculator. So here in example 10, we have 8 to the 2/3 power. So I want to talk about what that 2/3 power means. So this 3 in the denominator is still our index, just like it was before when we had the nth root of b equaling to b to the 1 over n power. That n here is that index. And so here, since 3 is in our denominator, that's going to be an index. So this will be a cubed root. And the 2 here is our power just like it normally would be. And I want to go ahead and rewrite this 8 to the 2/3 actually back into a radical form so that we can see that cube root. So what this ends up becoming then is the cubed root of 8 all to the 2nd power. And that's happening because that 3 in the denominator of our fraction is equivalent to our index. So I can rewrite this as then the cubed root of 8, and then that squared is already there in the problem, so it's still there when we rewrite it. Now the reason I have the cubed root on the inside and not on the outside is it's easier to simplify a smaller number first. Technically this is equal to 8 squared and then the cubed root of that, since multiplication is a commutative property. But it's easier to simplify a cubed root of a smaller number first and then make the number bigger, versus in the second way over here, I would square 8 and then cubed root that, which is just going to give me larger numbers. It can still be done and I'll still get the same answer, but it's a little bit easier, especially if I don't have a calculator, to simplify smaller, to make numbers smaller before I make them bigger. So I'm going to work off of the cubed root of 8 squared. The cubed root of 8 is equal to 2. So I have now 2 squared, and we know that 2 squared is going to be equal to 4. And we'll get that as our final answer. Now if we work off of the other method, we would take 8 and square that, and so 8 squared is equal to 64. Then we'd have to figure out, well, what's the cubed root of 64? And that is equal to 4 as well, but sometimes it's just easier to work with these smaller numbers. Now example 11 is similar. We have 4 to the 3/2 power. So here our power is this 3 over 2. Which one of these is the index? Is the 3 the index, or is the 2 the index? So in this case, the 2 is the index, since it's in the denominator of the fraction. That's what makes it the index. And the 3 is actually the power. And just like we did in the prior example, we can actually rewrite this from exponential form into radical form. Since our index is 2, that means I have a square root. So we'll get the square root of 4, and then we'll cube that. Why don't you guys simplify this down by simplifying the square root of 4 first, and then cubing that number. So to simplify this, the square root of 4 is equal to 2. Then we know that 2 to the 3rd power, 2 cubed, is equal to 8. And so we would get 8 as our final answer. We're going to see problems like this that do pop up as we continue on with this unit, so I did want to kind of slide in examples 10 and 11 here just so that we can see these while we're working with converting back and forth from going from radical form to exponential form or exponential to radical form.